GCDs and linear combination. We need groups for this. So what is a group? What is a group? Okay, a group is some set, let's say elements A, B, C, D, E, F, G, and so on, some set of elements. And also a way, I'll draw a box for this. This is a way to combine the elements. All right, it's a set of elements and a way to combine the elements. So I can take, let's say, two elements A and B from G, and I can combine them like this, A combined with B. And this is going to also be in G. This is my first property. It's called closure. So if I take two elements of G, I can combine them, and I'll get another element of G. 2, associativity. It's a long word. Okay, if I take three elements from G, I can combine them this way, A and B first and then C, and that should be equal to first combining A and B should be equal to combining B and C first and then A. That's associative law. For our case, we're going to be using addition and multiplication for our operations, so everything will always be associative. 3, we have an identity. There's a special element E in G, such that E combined with an element A from G will give me A. So it doesn't change A. E combined with A doesn't change A. And 4, if A is in G, then A has an inverse. Call it A bar, also in G. What is an inverse? Well, A combined with A bar should give me the inverse. Think about it. It's like combine 1 times 1 over x, give you identity 1. Inverse, and here's your element. Think of it like this, analogy. Okay, so this is like generalization of many things that we have already seen in algebra into an abstraction called a group. Okay, now let's take a concrete example. Integers. Z is a group. All right, let's see if this is true. Let's do closure. Let's take A and B are two integers. Okay, it's a group with what? What operation? Well, for our operation, I'm going to take plus. It's an additive group. Okay, so let's combine A and B by plus. And of course, if I add two integers, I get another integer. Of course, so that's no problem. 2, associativity. Okay, take three elements of Z, three integers from Z. If I add it this way, there is no difference than adding it the other way. Okay, like so. So it's associative, no problem. The plus is associative. These elements combine in an associative way. Next, identity. There's a special element in Z that behaves like identity, like this. If I combine it with E, it doesn't change, A. And what is that special element? Well, it's 0. Watch. If A is in Z, 0 plus A is A for all A in Z. So 0 is my identity. Now 4, inverse. If I have A in Z, then I have, this has to kind of look like a Z with like two lines, like so. If I have A in Z, then I have my inverse. What's that? It's minus A. Watch. A plus minus A, if I combine them, I get 0. This is the same thing like we did here. Compared to what we did before. A composed or combined with A inverse is identity. You see, it's the same thing, see? Here's my integer A, my operation is plus, my inverse is minus A, my identity is E. There you go. So I have all, let's try to fit it all in. I have all properties for a group. So therefore, Z is a group. Now, other things which are groups is this. Multiples. Multiples of D. Let's make a set. Call it DZ. Something like this. 0, D, 2D, 3D, and so on and so on. And backwards, minus D, minus 2D, minus 3D, and so on backwards. I can call this the group of multiples. Group of multiples of D. Why is it a group? Let's prove it. 1, closure. All right, so I have two multiples here. Let's take two elements, P, D, and Q, D. They're both in DZ. I should write it in that way with the double line like that, yeah. And if I add this together, PD plus QD, I combine them together. This is the same as P plus QD. And so therefore, this is an element of Z because this is a multiple. Multiple. This is a multiple of D, you see. So therefore, it's in DZ. So therefore, DZ closed. Okay, it's closed with respect to this combination plus 2. Associative. We know it's associative. Plus is associative. Okay, I'll wait. Let's do some hand waving there. Plus is always associative. 3, identity. Identity, easy. Okay, take P is 0. So we have P, D. This is 0, and that's got to be in Z and DZ. And this obeys the same rule as the identity as we saw here. Okay. Any other instance here, any other element, 0 plus Q times D is going to be Q times D. Okay. Where QD is in DZ. Okay. Now, 4, inverse. If PD is an element of DZ, then minus PD is also an element of DZ. Must be, it is in DZ because this is a multiple. This is also a multiple of D. And therefore, I have PD plus minus PD. This is 0, my identity. Okay, and so I have inverses of every element PD. I have an inverse minus PD in DZ. So therefore, DZ is a group. Okay, great. DZ is a group, and very interesting little point here. Interesting to think about this. Take D equals 1, and I have DZ. Now it's 1Z. What is 1Z? Well, 1Z is all multiples of 1. That's the same thing as Z itself. That's just interesting to think about. We may use this idea later on when we're thinking about coprime numbers. Let's keep this in mind. It's a very interesting idea. All right, so that's it. A group has 4 properties. All right, closure, associativity, identity, and inverses. Okay, inverses. Okay, and Z, where's Z? Z and multiples of Z are groups. Okay, so that's it for this video. If you like this, click like, subscribe, leave a comment. I will continue this idea in the next video. We're going to look at linear combinations, and we're going to prove a very important theorem about numbers, that every subset of Z is a certain type of group that can be expressed a certain way. A very, very interesting theorem.